Let's move on to enriching word vectors. This was also an assignment for you to watch, the corresponding video. This first half of the slide is just what we covered right now. You have a bunch of words, you write down a loss function for your skip gram model. You could end up being in a perfect case scenario end up using softmax function. This is perfect, but then there is an issue. W could be large. To deal with that, you're gonna do negative sampling. You show it a positive case, and you show it a lot of negative cases, maybe a handful of negative cases, around 12 or something. And then you write down your objective function. We learned how to include combinations of words like New York or any other combination of words. Can you actually work with subwords? Can you include them? And the only thing that you're going to be able to change is this scoring function. Let's try to do that. For each word, for instance, where, you're going to look at its 3 grams or 4 grams or 5 grams. And what are those? For instance, WH, in addition to this beginning of the word character, is a 3 gram. WHE is another 3 gram. HER is another 3 gram. And gram here is just character. And then you're going to have another one for your entire word. In this set, for each word, not only you include 3 grams, not only you include 4 grams, 5 grams, and 6 grams, you're going to include the entire word as well. So now each word is going to turn into multiple subsections, including itself. You can think of it as subsets of a word in terms of characters or subsequences. Now this scoring function, you're going to change it. What are you doing? You're representing each word not only with a single vector, but with multiple vectors. And you're denoting them by z's. There is a vector for where, there is a vector for every single 3 gram, every single 4 gram, etc., constituting that word. And then that's going to be your score. You're going to multiply it by the output representation. So this is just your word. It's a summation of a lot of vectors. And then you're going to train that. Now what you're training, what did we just do? We turned each word in our vocabulary, which was around millions already, we turned them into a lot more. Maybe we are increasing it by 10-fold to represent these subwords. And then this is important for languages where you have a lot of combination of subwords giving you new words, like German, like Turkish, like Italian, like French, English to some extent, Czech a lot. This is, for instance, German words. Why is it useful? Because now if you see a new word, for instance, kindness, and it's not part of your vocabulary, but you already have a vector for kind, you already have a vector for ness in your vocabulary, you're just going to add them together. And that's going to give you the vector representation for kindness. And this is the way that you're going to deal with new words in your dictionary, or the words that you haven't seen before. And you're going to start to see some nice patterns. For instance, pre-adolescent and young, you can see that there is a very high correlation between adolescent and the young. If you multiply them together, that's going to give you the score. And the highest score is the most red one. I think I'm finishing right on time. For those of you who have questions about subword information, I'll be around. For those of you who want to leave, you can leave. Next session, we are going to do classification.
So, Joe, like the previous results, won't the actual values depend on the exact data that is being trained or analyzed on?
Data matters, definitely.
Yes. So the things like, the 300 and the values of K and stuff like that, doesn't it actually depend on the words? Because it might happen that, each data will have a different distribution of words and everything, right? So that'll affect the values of the graphs that you showed.
No, absolutely. So data matters a lot.
Okay.
Usually I start the deep learning course by saying that data is the source code for deep learning.
Right.
And those numbers, those hyperparameters and the parameters of your model depend on the data.
I see. Yeah. So my question was, there's no actual way of knowing what's a good near optimal values of K that we can use for that negative sampling?
No, but then the way that you're going to fix that problem is you're going to set aside some validation data. In this case, what was our validation data? those
Sorry.
syntactic, and semantic analysis tasks are actually your validation data.
Okay, I
You
see.
look at your validation data, and then you're going to pick the model or pick the hyperparameters that are giving you the best performance on them.
I see. Okay.
So
And
not
what's
only
the
the training data matters, but also the validation data matters.
Yeah.
Okay.
And what's the exact difference between the syntactic and semantic accuracy?
It's the same formula.
Yeah, I mean, so that's why I was confused too. I mean, formula-wise they are same. So what's the actual difference?
The actual difference is one of them, the semantic analogy task, requires your model to understand something about language.
Yeah.
And it's totally different from fixing the syntax. For instance, turning this vector into vectors. Maybe these are simpler tasks compared to understanding that there is a relationship between enriching and enhancing.
Yeah.
So this is a harder task, enriching, enhancing.
There's a good example in the efficient estimation in paper number 3. There's a table of 5 types of semantic tasks and 9 types of syntactic tasks.
Okay.
Yeah, so these are syntactic and these are semantic.
I see. Okay. Thanks a lot.
Can I ask a little more about the hierarchical softmax, just to straighten my understanding, right?
Yeah, sure.
So I think I'm confused by the architecture on the very left. So we start everything with the one hot encoding and then pass everything together through an embedding matrix to get embedding vectors, right? And then to calculate the softmax or hierarchical softmax, that's just how you construct the loss function. It's not really flowing the way that in that graph.
No, so this graph here is different from this graph here.
Yeah, I think I'm totally misled by that architecture drawing.
Yeah, so this architecture is telling you that let's pick an input word, let's say representations, and then let's predict the one word to the left or 2 words to the left and 2 words to the right. So that's the idea. Maybe off is a better example. Pick off, predict representations distribution, pick off, predict words, and. So that's the idea of this figure.
So by the time to calculate the loss, I'm using only embedding vectors. It's from everything that is already converted. And to use a hierarchical softmax, are each of those node also a trained parameter? Can I understand that way? Okay, now that totally makes sense. So they're all parameters trained, stored somewhere, and I need to know ahead of time how many nodes I need based on the size of my vocabulary set those up. Okay, now that makes sense.
So let me combine this figure and this one, then you're going to understand it even better. Let's pick this WT, let's call it WI, and that's going to be this vector representation that you have here. This is this vector, this other vector, and this other vector. Okay. So in this formula, we just found out what are these guys. Now let's find out what is the output word. Maybe let's predict this first word here. That one is going to be WO, correct?
Right.
You look at your dictionary, there is going to be somewhere in your dictionary, there is going to be WO. You found it, okay? This is your output word. You trace it back to the root. What is the path that I need to take to end up at this node, at this word? And then previously, you only needed what? You only needed one vector for this output one in this loss function. For this other loss function, you need to know the vector representation for this node, the vector representation for this other node, the vector representation for this other node. Why is that? Because then you can plug them here. You plug the root node here, the other node here, and the other one here. Now you know everything.
Right.
Therefore, you can write down your probability.
And now you only need to do this, evaluate 3 dot products because you're using sigmoid instead of softmax.
Exactly. So
And
this is
that's the
going to end
point.
up, where is 3 coming from? It's the log of 8, log 2 of 8. 2 to the power 3 is going to give you 8. And 8 is actually the size of your vocabulary in this case.
What happens if the vocabulary, there's like some leftovers, it's not a 2 to the certain power?
That's fine. These corner cases, that's actually a choice that you make. Pick your W so that it's to the 2 to the power something.
Okay.
This is a hyperparameter. And even if it doesn't happen, there is going to be a note here hanging that it's going to have its own path.
Like a blank padding sort of thing.
Yeah, maybe you can just put it here.
That totally makes sense now after thinking about it really hard.
Yeah, and you had the correct point. Here you need to multiply 3 terms. So you need to have a for loop that loops only 3 times versus a for loop here that's going to loop 8 times. And
Do we
that's the
have any
difference.
convenient built-in function for this?
Yeah, so these are implemented. Hierarchical softmax is implemented in PyTorch and TensorFlow.
Okay, I'll do some research.
The same way that softmax is implemented, hierarchical softmax is also implemented.
That's a relief.
But then you're going to be using negative sampling most of the time. So this is the one that I want you to definitely learn.
Okay.
Okay.
Thank you for confirming that, and thanks for explaining everything.
No, sure.